Hey, what's up, everybody? So, day 2 of the lessons. We're still on this week 1 for the Model 1, the classic linear building automation optimal start with simple degree per minute type lesson. Still in the easy section, so I think it's kind of hard, but still in the easy section. So, all right, let's get into the specifics of it. So, jumping around here on the repository. So we're still in this delta temperature and calculating a rate. Just going down here. So we're here. So this will be the lesson. So day 2, the formula T equals the delta temperature, which would be the zone and the zone set point difference and the rate of how in time. So look at more some of the raw math and predicting the runtime if you know the rate. So jump into the specific lesson. So here we are, the linear formula refresher, y equals mx plus b, slope of a line. Alright, I'm just going to read through this a little bit, what yx plus b really means. Y is the predicted warm-up time t in minutes. So x is the delta temperature, sometimes referred to as t squared in Model 1, which we'll get into later. Or Model 3, that also incorporates weather, and m is the slope, b is the intercept. So it's written as T equals A times delta T plus B. Here A equals degree per minute, and which is just the slope, and B is the minutes, it's the intercept. How it applies to optimal start. So if a building warms at 0.2 degrees Fahrenheit per minute, the inverse is 5 minutes per degree, which would be a linear warm-up model. Which makes sense. So for every degree that you're off from zone temperature and set point before building warm up or cool down, you would just add in this fixed rate. Completely linear. Solve a linear model by hand for 2 points. Alright, so I think in micro lesson we'll get into a little bit of this. Calculate the slope. So we'll calculate the minute per degree. So if we were off by zone set point one day, it took 15 minutes to warm up, and then let's say a different day we were off by 6 degrees and it took 27 minutes to warm up or cool the zone, that would equal to minutes per degree. That kind of makes sense. All right, here we go. So day 2 micro lesson, compute the slope. So this is our data here. So we'll end up computing degrees per minute, compute the intercept, compute B, and predict warm-up time. All right, so this is what we'll do. Maybe I'll just copy this. I might copy this right into Python. Here's my Python file. Just gonna save this just so I can see this data and use it as variables. Okay, so jump back here, compute the slope. Alright, so let's compute the slope based on degrees and minutes for two days of data. So this could be warm up or cool down. It took 14 minutes one day, and a different day we were off by 7 degrees and took 32 minutes. So we have to compute the slope. So and I think it's important to just also note that we would want to have separate rates for heating and cooling. So if we're in a heating application, we would have a completely separate data set for heating, and switch to summertime, and we're in a summertime application, we would have completely different data for summer. Because there's different, the physics, it's a little bit different for heating loss and cooling loss. That's why we'd have in our optimal start blocks, so we'll get into later, we have different data for heating recovery and cooling recovery. Okay, so let's dive in, compute the slope for this. So a little bit of data here. All right, so let's just do delta 1 equals, let's see, how can we do this? So we could do 3 delta 2 equals 7. We could do time 1 equals 14, and time 2 equals 32. So that's this data here. Here's a 3 degrees, 14, and then here's our 7, and then our 32. So let's compute the rate for degrees per minute. So we're just going to go into our equation, which was m. So if we want to do minutes first, we would do, let's see, time 1 minus time 2 divided by delta 1. Oops, actually I forgot my quotes. So delta 1 minus delta 2. Let's print this, print m. Let's see what this comes out as, Python. So 4.5, so this would be in minutes per degree. So this would be, that makes sense. So like approximately 4.5 degrees per minute. So if we were off by 3 degrees in cooling or heating zone recovery, 4.5 degrees, about 15 minutes. So that looks about right. So the next thing we need to do is compute our intercept, which is b. So this is kind of incorporates the lag, I think, in the model. So let's do b equals, so I think we can just pick one of the data points here. Let's see, so let's do time 1. Let's see what we do for m again. So I think, yeah, so this will be minus m times delta 1. Okay, so let's see what b. .5 is what I'm coming up with. So let me think here. So minutes 1, delta 1. All right, so that's our intercept, which is not a lot. So this should be in units of minutes too. So that's incorporates like lag in the system. So like even though it's fake data, it would be what we would add to our calculation to account for a little bit of lag in physics. So like if you energize a cooling coil or turn on a boiler or a chiller, there's like some lag in the system that will take before you start seeing the effect on the temperature sensors. So this is what our intercept B would account for. And then the last thing that we want to account for is predict the warm-up time. So if we have, I'm just going to compute this. So if we're off by 5 degrees, let's let's use our model to predict it. Okay, so then we would just need to do t equals m times 5, which is our new model that we're off by, or new data point that we're off by, and then this should be our warm-up time that we'd be needing to compute. So okay, so I might just call this like, let's call this like delta 3, because that's 5. It just makes a little bit more sense, I think, when there's like variables that you can call it by. So 23 minutes. All right, I think that kind of makes sense to me. I know this stuff is a little bit easy at the moment, so I think it'll get really hard really fast. So like another thing like I think I might do actually is on these lessons is even have AI kind of see if just let me know how I'm doing. So I think at some point in time, the stuff I know for a fact, because I don't have like super advanced math background, so I'm going to be asking, probably chatting with AI to be like, help me, I'm stuck, I don't understand, I know it's coming. And then also have it, grade everything. So I'm just going to be like, can you assess day 2 lesson, please? See how it did. So I know this stuff is pretty easy. So full assessment, day 2, your classic stuff. So pretty easy. So did excellent. All right. So your setup initially, so we're building just these simple linear models. So we calculated the slope, which is m 4.5. intercept, which was b, and predicted 5 minutes with the model, so the math is correct. Your rate is not constant. All right, so this is telling us where linear models might fall short. So when we get into the more complicated models, this will in theory have better performance. So hopefully this makes sense, guys. We're just kind of getting into some of the mathematics that runs behind these optimal start blocks. And technically, like on the last video that we decompiled the tritium's optimal start block, this is pretty much the math behind tritium's what's built into kick control. It's just yesterday's data, the last performance, and we'll just basically kind of fine-tuning it based on only one day of data. But these more complicated models will start having 10 days worth of data, and the theory will get better results. So that's all for this one. I hope to see you on day 3.